Anyway, this all started off back in the beginning of the year when we had a committee meeting, and we were just trying to sort out the planning the speakers for the main meetings for the current season. And of course, at that time, James Webb had just launched. And today's slot, or the May slot, was designated for the regular chairman's address. So I thought I had plenty of time to get the presentation together. I actually finished at about 5 o'clock this afternoon. So it's I started off quite early after that meeting, so getting the skeleton put together. But of course, the thought was that having launched on Christmas Day last year, if all goes well, hopefully there'll be some good science coming from Webb in June, July of this year. So I thought it was a good topic for today's address. So I'm sure you're all familiar with the James Webb Space Telescope. And in our first graphic here, we've got a view of the cold side. So the optical telescope elements on the cold side, with the integrated science instrument module, which we don't really see in this image, behind the main mirror, and protected from the sun by the tennis court size solar shield. And we've got an artist's impression here of the hot side, and if I get this right, what we can see just around here is the solar panel, and here's the radio antenna, and so their deployment fairly shortly after launch was a critical event for Webb. If they hadn't deployed, it would have been possibly the end of the mission. So who was James Webb, which the telescope's named after? So he was the administrator of NASA from 1961 to 68. And as the slide says there, played an integral role in the Apollo program. So the James Webb project was actually started in 1996, and it's been an international collaboration since the beginning, mainly led by NASA, but in partnership with the European and Canadian space agencies. And it was originally envisaged the launch would be back in 2007, but there was a major redesign undertaken in 2005, which put back that date. And there have been a number of setbacks along the way, but construction was finally completed in 2016. An extensive period of testing work began, but again, that was delayed by the COVID-19 pandemic. But finally, it managed to be launched into space on the 25th of December, 2021. So another graphic, which here we can see a bit better, the solar panel, the stabilizing array, the antenna, the sun shield, and the 18-segment primary mirror with the secondary on some 8-meter booms there, with the instrument pack, as I said before, sat behind the main mirror. So the mission in a nutshell was basically, it goes beyond what Hubble and other space telescopes can, by seeing things that they cannot see. So at the end of the dark ages, this first light and reionization, the assembly of galaxies, and the formation and the evolution of the galaxies, birth of stars and protoplanetary systems, planetary systems, including our own solar system and exoplanets, and the origin of life. So James Webb Space Telescope is about beginnings, the beginning of the galaxies, beginning of stars, beginning of planets and life. So sometimes referred to as the next great observatory, it's the scientific and technology successor to HST. HST has looked deeper into the universe than any other telescope before it. And it took HST more than 3 continuous days to do one of those real deep views. But Webb will do that in will do a similar image in less than an hour. It's more than 6 times the collecting area, or the light collecting area of HST, 100 times more sensitive, and 1,000 times more sensitive than Spitzer was. It operates at 40 Kelvin, so that's roughly minus 387 Fahrenheit or 233 Celsius. And it operates in deep space, about 1 million miles from Earth in orbit around the L2 Lagrange point. So it's 4 times further away than the moon. So how does it differ from existing space telescopes? It's bigger than Hubble, as I just mentioned, which has been orbiting since 1990. Hubble's main mirror is 2.4 meters, so that's 7'8" across, while Webb has the primary mirror that's 6.5 meters, so that's 21.3 feet in diameter. With all the other associated equipment, Webb's about the size of a tennis court. It's so big, in fact, it had to be folded to fit inside the launch rocket. But the key aspect of Webb is it's tuned to detect light that Hubble cannot into the infrared. So this light's invisible to the human eye, but it's the type of light which the glow from the most distant objects in the universe will show up. So the earliest sources are so far Doppler shifted far into the mid-infrared, part of that spectrum as they race away from Earth. And in the graphic here, we can see this part of the spectrum that Hubble could see, the part of the spectrum that Webb's going to see, laser, and the part of the spectrum that Spitzer saw. So I try to keep the text-only slides to a minimum, but a few have remained, so please bear with me. So some of the key facts, you can see that it's diffraction limited at the 2 micron wavelength. We've got a 25 square meter coverage from the primary mirror. Our instantaneous field of view is about 9 by 18 minutes. And we've got deployable primary mirror and secondary mirrors, because as we said before, the size needs to be able to be folded up to fit in the launch vehicle. So we've got 18 segments of the primary mirror, and we've got 7 degrees of freedom adjustable on each of those, and we'll talk a bit more about that later on. The integrated science instrument module, containing the near and mid-infrared cryogenic science instruments, sits behind the mirror, and the near-infrared camera functions as the onboard wavefront sensor for the initial OTE alignment and the phasing, and it'll be used for periodic maintenance. The deployable sun shield for passive cooling, and our mass is just over 6,500 kilograms, which is about half that of Hubble. The power generation from the solar panels, surprising. I'm surprised how low that figure is at only 2 kilowatts. But more on that again later. And the onboard data capabilities, I think is probably being limited by the amount of data that they can send back per contact session. So launch vehicle was Ariane 5, and the initial mission duration was thought to be maybe 5 to 10 years. We've already talked about that. So another fun fact here, we've got the primary mirror, which is made of beryllium, but it's coated with gold. So we know the area of the 18 segments, and given that the gold coating is only about 1,000 angstroms thick, so that's 100 times 10 to the minus 9 meters. using these numbers plus the density of gold at room temperature, which is, as everybody knows, 19.3 grams per cubic centimeter, the coating is calculated to use 48.25 grams of gold. And that's about equal to the mass of a golf ball. So there's a pub quiz answer for you. The golf ball actually, its mass is 45.9 grams apparently. Not that I'm a golfer, but I'm sure the golfers out there would know that. And the final key fact, the size again of the Sun Shield, 21 meters by 14. And the 5 layers with the maximum temperature on the sun facing side at a fairly hot 230 Fahrenheit or 383 Kelvin. But by the time you get to the layer 5, the temperature can be down as low as minus 394 Fahrenheit. And the operating temperature in general is going to be under 50 Kelvin. So I realize now I'm missing the Celsius numbers on there, but never mind. So there have been some major innovations along the way for the project. So the lightweight optics, and a lot of that is down to the fact the mirrors are made from beryllium. So it's perhaps the lightest metal out there, having it's only number 4 on the atomic table. I nearly went into quite a bit of detail on the beryllium and the mining. There's some great sort of YouTube clips out there, but that would probably be diving in a bit deep for this presentation. And obviously 6.5 meter diameter mirror would be too large to construct, and you wouldn't be able to fit it in any launch vehicle. So that resulted in, of course, the folding segment mirror option that Webb has. And again, the mirror control, these cryogenic actuators and the mirror control, that was very much a lesson learnt from Hubble. So if you all recall, when Hubble first launched, the mirror that's of the 2 mirrors that Perkinel made, the one that went into orbit was defective and the flight spare on the ground was perfect. So it took a servicing mission to go and fix that problem. And of course, with Webb being out at the L2 Lagrange, there's no possibility of a servicing mission. So they reused one of the Apollo chambers to put Webb in to give it a taste of what it would be like to operate in deep space. And I think at the time they were doing this, there was some massive storm hitting the area in the States, and so some of the kit outside was they were having to cover things in plastic to make sure that rain coming through the ceiling didn't disrupt the testing. But fortunately, Webb being tucked away in the vacuum chamber was safe from it, demonstrating it didn't have the Hubble problem. So what was interesting, even at this stage, was the understanding of what they were going to see, because they were able to, as you can see here, the mirrors are deployed and the secondary mirror on the boom all do actually fit inside the chamber. And what they knew, oh, sorry, let me go back a slide, wrong slide here. So they knew that when they first focused the system, that they would see 18 different spots of light, because of the 18 individual mirrors wouldn't be aligned, but they'll then adjust the mirrors to bring all the spots together. And I've got some animations that show exactly how that happens a bit later on in the presentation. So Webb was placed in the Chamber A on the 20th of June 2017 to prepare for a 3-month testing in that cryogenic vacuum that mimics the temperature of space. And the chamber can simulate an environment where the telescope experienced extreme cold of around 37 Kelvin, so that's minus 236 Celsius. And of course, in space, the telescope must be kept extremely cold in order to be able to detect the infrared light from very faint distant objects. So here's another shot, and again, the technicians in the foreground give you some idea of size. And this was the same sort of configuration it would have in space. But that's gone through a test where they'd fully unfolded and deployed the mirror. And that test occurred in March 2020 at a clean room in Northrop Grumman Space Systems in Redondo Beach, California. So I mentioned on one of the early slides that there was a big collaboration, and of course Europe, ESA, made a contribution. So although it's now, the budget is looking like it's 10 billion US dollars for the whole project. Actually, somebody's done a calculation here and says that for Europeans, the cost to Webb has amounted to the price of a cheap cup of coffee. So, and that's a cheap cup of coffee served in a cheap cafe, drunk over a period of 20 years. So hopefully we'll see some good value from the science that it produces over the coming years. So again, here we can see the primary mirror sort of folded up a bit like a trestle table. And another test where they've got the Sun Shield has been deployed, but yeah, it's another day at Northrop Grumman. But Webb had a bit of a troubled past, and I didn't go back too far, but we can see that the costs started to spiral back in 2010. They thought it would cost 6.5 billion, and then in 2011 there was a bit of a fight in, I think, the Congress in the US. There were people calling for the cancellation of the mission, but fortunately NASA prevailed. But then shortly after that, the price tag went up to over 8 billion. And in 2012, one of Europe's, in fact, one of the UK contributions, the MIRI instruments, was complete and shipped off to the US. Shortly followed, almost a year later, by the second European contribution, the near-infrared spectrometer, which was built by Airbus. March 2018, another delay for the launch, and then June, another pushback. But in November of 2021, a report saying that it was going to be easily worth the 10 billion cost that it has now reached to. And on the 29th of April this year, one of the news items was Webb's in its final stretch of its commissioning phase. I'll have a quick look at some of the observatory hardware in a bit more detail now. So the overview of Webb showing the, do you keep using this? So we've got the hot side, and we've got the cold side down to around 40 Kelvin. So it's comprised of the, on the hot side, we've got the Spacecraft Bus, and that's going to manage the power and a number of things. And actually the value, or the radiant power, if we've got 200 kilowatts of energy radiating from the sun, only 1 watt of that gets transmitted from the hot side to the cold side of the Sun Shield. And by radiating the sun's energy to space, the Sun Shield allows the OTE, that's the optical telescope element, and the ISIM to passively cool to cryogenic temperatures without the use of expendable cryogens. So I think I briefly mentioned that the solar array was one of the first of two sort of time critical milestones, the second being a first mid-course correction burn, and both of these happened shortly after launch. And if it's successful later on, I've got a short video where we'll actually see that solar panel get deployed. Couldn't find many images of the solar panel. I was a bit disappointed in finding a source of good ones for this, but yes, it's a 20-foot array that sort of folds up like a bit of like an accordion, as they often do. And it was set to automatically release shortly after launch. Now, I mentioned on one of the key slides, the key fact slides, that the solar panel can generate 2 kilowatts. But to my surprise, I found that Webb actually only uses 1 kilowatt of power. The panel is capable of creating double that, but the amount it's sort of been factored in for gradual wear and degradation of the panel being in a harsh environment. And obviously the power it creates operates the telescope propulsion, communications, as well as all the scientific instruments. So it's like that single source. So in order for Webb to detect the infrared from faint objects, the telescope and science instruments must be cooled to about 40 Kelvin. And as I think as already said, this cooling is done passively by the Sun Shield. And I think in our next one, we'll see basically the heat gets bounced around between the layers and sort of dispersed out the side. So very little. So I said, 200 kilowatts in, 1 watt out is not a bad bit of protection. So the solar shields are sort of diamond-shaped system of 5 layers, and it's an aluminium-coated polyimide film called Kapton. So some people with 3D printers might be familiar, because you often will find Kapton used as the on the plates to print your objects on. And Kapton was developed by DuPont in the late 60s, and it's a very high resistance to heat and remains stable across a wide range of temperatures, so dimensionally stable, that is. So it can tolerate from -269 to +400 Celsius. It doesn't melt or burn at these high temperatures. So on some of the layers, oops, go back to the right one. There's an additional coating, I think, on layers 1 and 2 with so it's got the coating of aluminium and a coating of doped silicon. And those 2 layers, or that doping, results in a slight pink tinge, which you'll see in some of the pictures. Right. So now on this view, we can see the OTE, and the 18 segments are sort of grouped into 3 different categories. So we've got the 6 that are labeled A1 through A6, we've got B1 through B6, and C1 through C6. I think they've all got a very slight different optical characteristics, but we'll see how they get combined together a bit later on. So it's basically a 3-mirror anastigmatic design. So we've got the primary mirror, we've got a secondary mirror at the end of this boom, and then inside the assembly there's a tertiary, the 3rd mirror, and then the 4th flat mirror, which is used for fine steering and used for pointing, stabilization, and small offset maneuvers. So the effective focal length is the focal ratio is f20, and the effective focal length is a stunning 131.4 meters. So the mirrors are made from beryllium, which is both lightweight and very stable to temperature variations over a range of 30 to 80 K. The mirrors are coated with gold to provide high reflectivity from 0.6 to just beyond 28 micrometers. And the main components of Webb are labeled above, as we saw. Unseen on the backside are the mechanisms of electronics for active control of the optics, plus the primary mirror backplane support structure, which provides a rigid framework. And this photo shows the OT in a large clean room at NASA's Goddard Center, and this was taken in October 2016. So that would have been just after it was completed. So as mentioned already, made of beryllium. It's a rare lightweight element metal used as a primary material throughout Webb. I can save that one. And here we have, for scale, just one of the segments. Obviously, this is the rear view of the segment. And here we can see the guys inspecting the just one of the segments. And for comparison, compared to Webb, comparing Webb to Hubble, the expected lifetime for Webb is 5 to 10 years, but more on that later. As already mentioned, 6.5 meters versus 2.4, but the mass of Webb, even though it's a much bigger telescope, it's half that of what Hubble was. And whereas Webb's going to operate in extreme cold of minus 230 C, Hubble was operating around 20 C. And again, another size comparison from a human next to the Hubble, and obviously Herschel, which was looking much deeper into the infrared than either Hubble or Webb will do. And we'll see an animation of this a bit later on, but the wavefront sensing and control is going to keep the primary mirror segments aligned and in phase so that their wavefronts match properly, and the segments will then act like one large telescope rather than 18 individual telescopes. So the telescope commissioning process after launch will proceed through several stages of iterative sensing and alignment correction over several months to establish the initial best on-orbit alignments. And routine monitoring, observations, and occasional corrections during science operation will subsequently maintain the mirror alignments. The wavefront sensing results will be made available in the archive for use by observers for any data calibration or analysis purposes. So there's going to be a lot of data generated. Now, the momentum management, I think if you're interested in this, the best thing to do is go look it up on the website, because there's so much scientific detail on this. But basically, momentum is managed both predictively in real time by the active control system to keep the observatory under control at all times. But during the observations, the solar photon pressures against the angular momentum build up within the reaction wheels. And so they have a process of getting rid of that angular momentum by sort of doing what they refer to as a dump periodically by firing the thrusters. But if you're interested in that, I've got some URLs listed at the end of the presentation if you want to do a bit of a deep dive into that. And again, for scale, I've got this image with a technician working on the ISIM. So it's the main structure that houses the 4 scientific instruments. And again, this was showing its final preparation in the spring of 2016. But that previous image wasn't quite complete because this instrument over on this side over here wasn't mounted on that previous shot. So I think this shot shows them it's sort of fully integrated. Couldn't find an image for this, but as I mentioned briefly, that it's got a solid state recorder, can record 65 gigs of science data, and the science data downlinks, which occur in 2 4-hour contacts per day, where each contact can transmit at least 28.6 gigs. So I suspect it was the data rate that sort of limits the size. And this is a sort of field of view showing various instruments from NIRSpec, NIRCam, MIRI, and the NIRSS. But the main reason for this is the fine guiding sensor. So these would be the sensors that are on the focal plane, which provides data for the science attitude determination, fine pointing, attitude stabilization, and using guide stars for the in the Webb focal plane. And another graphic showing the optical layouts. So light from the, get the laser pointer. Oh, no. So light will come in and bounce off this pick-off mirror, which will then come into this 3-mirror assembly. I think it then will exit and come off the fine focusing mechanism and come into the detector assembly with the FPA arrays. And then there's another one here I want to point out again for later on, is here we've got a guider, something they call the sidecar ASIC. So remember that term, we'll come back to that. So it's got 3 modes of operation. It can be off, it can be in standby, or it can be in operate mode. So in operational mode, it's got 5 software functions: calibration, identification, acquisition, track, and fine guide. And the calibration function allows the FGS to obtain necessary data for calibration by the ground system, while the remaining functions enable the identification, acquisition, and tracking of a guide star. And unlike HST, the fine guiding sensor on Webb are expected to be used exclusively for guiding and calibration. And at this time, there's no plans for them to be used for other science proposals by general observers. And here we've got a view of what they refer to as the Spacecraft Bus. And this is responsible for providing electrical power, communications, attitude control, thermal control, and health and safety functions for the craft, the command and data handling, and communication services, as well as propulsion for orbit insertion, orbit maintenance, and as I mentioned before, the momentum unloading. And the Spacecraft Bus is located on the sun-facing side of the observatory and operates at a temperature of about 300 Kelvin. So it's also home for 6 major subsystems. As I mentioned, the electrical power, attitude control, communications, command and data handling, propulsion system, and thermal control system. So a lot packed into relatively small space. I think it's about 3.5 meters. So the solar panel, the green part, is about 6 meters. The main part of the spacecraft bus, I think, is about 3.5 meters. Now, these are something which I find to be absolutely amazing pieces of engineering. These, what they refer to as the Cryogenic Nano-Actuators. So these are what allow them to position the mirrors to extremely good accuracy. And the design incorporates basically mechanical components, so there's no, other than a motor, there's no electronics on this at all, and it gives you an amazing, an actuator that can give you 10 nanometer positioning resolution, but over a 20 millimeter range. So when the mirrors are packed and stowed for the launch, they're all locked down, and they have to, move by about 20 mil to get into their operating position. And when they're in that sort of final extended position, they need to be able to be manipulated with nanometer accuracy. So there's plenty of YouTube or clips out there, but I do recommend one. There's a guy goes by the name of Breaking Taps, and he's managed to reverse engineer one of these actuators and has got the STL files if you want to make your own by 3D printing it. Again, links at the end. So I've already said the main mirror is made of 18 segments, and the position must be finely tuned to make it a perfect reflector. So each of these mirrors has got 7 actuators that move it through 7 degrees of freedom. The usual 6 that a Stewart Platform mechanism provides, and Mill Dave is going to provide us a description of what a Stewart Platform mechanism is any minute. Sorry, only kidding, Dave. But anybody that's been on a flight simulator will probably recognize it when you see the next image. So the simplicity that belies this ingenious mechanism that allows both coarse and fine adjustments over such a wide range of travel, and the clever tumbler mechanism that lets it switch from coarse mode to fine mode, and the flexure that's used for such fine adjustments is just, to me, it's just amazing bit of engineering. So there we go, Dave, you recognize that? So
certainly do.
This is what you might have, and you see them in all sorts of places now, in fairgrounds and the like, where you get simulators. But I think the first time I came across with one of these was obviously on a flight simulator. But basically, this is what gets you the actually 6 degrees of freedom. So we have 3 linear movements in sort of X, Y, and Z, so lateral, longitudinal, and vertical, and 3 rotations that provide you pitch, roll, and yaw. So the Stewart platforms can be known by a number of different names, but as I said, you've probably seen one somewhere. So I mentioned there's a 7th degree of freedom, but that's actually going to be the curvature of the mirror, which again is going to be adjustable for Webb. So again, sometimes different terms used. So tip equates to pitch, roll, tilt might be yaw, Y translation, longitudinal, X translation, lateral, or piston, or Z or Z, as the Americans might say, will give us the vertical adjustment. So what we have here is an eccentric bearing. So the motor shaft is, or the motor is going to be driving this thing here on, but it's slightly eccentric. So that's going to move, which makes this crossbeam go up and down. And the large movements there get translated into even finer movements on the top surface. And I said it's all mechanical. So the only thing that's powered is the stepper motor, because this has to operate down at 40 Kelvin. But there's a very, and again, if you do want to see this, it was too long to include in this pitch, but go watch Breaking into Tap's video on this, because it's amazing how just by this tumbler coupling, it can engage it either in a coarse mode, in which case you can get a travel of about 20 millimeters, or in the fine mode, where you've got nanometer control over the fine position surface. And they're generally arranged in pairs. So there'll be 3 of these mounted on the back of that, on each of the 18 segments. So again, lots of potential single points of failure, but they all seem to be working precisely as designed. So a few of the characteristics. So each of the instruments are going to observe an area of the sky that's bound by the coordinates given by this V2, V3 coordinate system. And we can see that they've got an area they call the field of regard. We can see our celestial sphere, so what the background stars that we can see. And again, this is going to be explained a lot better when we get to an animation shortly. But basically, we've got the 3 axes. We've got, if we think of V1 as like the bore sight, looking down the telescope. And in this particular case, V2 is coming out of the screen towards us. And V3 is what they refer to as the anti-spacecraft coordinate. But if we note, there's the origins, come on, where's the laser? So, and it's all referenced against this origin here. But again, we can see the basic light path of light coming in, bouncing off the primary, onto our secondary, through cascading focus, onto the tertiary mirror, behind the primary. Then there's a pick off here for the fine steering mirror, and then finally back out to the focal plane surface back here where the ISIM is going to be. And again, on this side, we've got a degree of movement. We've got a degree of movement that the spacecraft's able to maneuver, and obviously it can rotate 360 degrees around the sun line. And I think at this point, this is, and we've got another couple of, this V3 can move about plus or minus 5 degrees, as we can see there. So again, unfortunately, a couple more Sony slides, but what we talked about, Webb being placed in orbit at the L2 Lagrange points, but actually it's incorrect to say that it's going to be at L2, rather it will orbit around L2. I found another video which is a nice description of what they refer to as a saddle point, which is effectively what you'd have at L2. But the problem is that Webb must never go beyond L2. So they, it's always going to be slightly this towards Earth, because you can't turn around, you can't turn Webb around to bring it back closer. If they put too much thrust on it, then if it goes past L2, it's lost, because turning it around would destroy all the instrumentation because of the heat from the sun. So yes, from this, Webb is going to need regular firing of the onboard thrusters to maintain its orbit around 2. And these station keeping maneuvers will be performed every 21 days. So I think they'll do an assessment every 19 days, and then every 21 they'll make a correction. Sorry, no. So again, the Lagrange at point 2 is one of 5 gravitational sweet spots around the Sun and Earth, where satellites can hold their position with few orbital adjustments, thus conserving fuel. And the other thing about the orbit is it won't experience the big swings in temperature and light endured by space telescopes positioned closer to the Earth. And this, of course, is vital for the mission, as it's designed to view the cosmos in infrared light and must maintain, therefore, constant supercold conditions for the hardware. And again, the rationale for this particular orbit was it's easier to get the spacecraft to L2 as well as maintain its orbits. I won't read the whole slide. I think the key thing from this one is the fact that if they get the velocity right, the trajectory is such that Webb just falls into orbit around L2 rather than to having to forcibly inject itself into a set orbit using its propulsion system. And this obviously saves propellant and makes for simpler orbit maintenance. So here we can see the trajectory from Earth to the insertion into the halo orbit. And so we've got basically we've got 3 panels here. That's projected onto the ecliptic plane. And panel B is the view in the ecliptic plane, and C is a view along the Earth sun line. So we've got another short little clip here, which I shall try and get started. Don't believe there's any sound with this one. So the L2 orbit is a period of 6 months. And while the orbits around the L2 are inherently unstable, the orbit size is large and the orbital velocity is low. So it's less than or about 1 kilometer per second. So the orbit decays slowly. However, James Webb Space Telescope's large sun shield is subject to significant solar radiation pressure, which results in both a force and a torque. And the direction of the solar force varies as the observatory's attitude changes from observation to observation. So the solar torque is balanced by reaction wheels, but periodically the accumulated momentum is dumped by firing thrusters. Because James Webb Space Telescope operations are event-driven, the observatory attitude, profile, and momentum dumping cannot be accurately predicted months in advance. So these 2 permutations increase the acceleration of Webb from its orbit about L2, and that necessitates more frequent orbit maintenance. So the station keeping maneuvers that's the other Lagrange orbit missions, which are typically 3 to 4 times a year, but the accurate orbit determination required daily tracking measurements over a period of 19 days. So station keeping will be performed every 21 days. And so the next I got on that.
Can we mute Sky Badger? All I can hear is the keyboard going.
Sorry, apologies, didn't realize all.
Thank you.
Right, so now we'll have a quick look at the different instruments in the suite. So we've got NIRCam. It's an infrared imager from the edge of the visible light through the near infrared. So the wavelength it's going to observe in is 0.6 to 2.3 microns, with a field of view of about 2.2 arc minutes by 4.4 arc minutes. And it looks something like this. And this is in a clean room at the Goddard Space Flight Center. It was built by the University of Arizona and Lockheed Martin. So again, near infrared camera covering those wavelengths, 0.6 to 5 micrometers. And it's also used to provide key measurements for the in-orbit adjustments of the shape of the primary mirror segments. And it's the observatory's primary camera that will require some of the deepest near-infrared images ever obtained and to detect light from the first stars and galaxies, I hope. It's also got a coronagraphic and spectroscopic capabilities, which will be used to characterize exoplanets and planetary systems. So that's NIRCam. Then we got NIRSpec, which again, near infrared spectrograph. And it performs spectroscopy over the same wavelength range as NIRCam. So again, that was 0.6 to 5.3 microns. And the same field of view, 2.2 arc minutes by 4.4 arc minutes. And now we've got the near infrared spectrograph, and this is provided by ESA, with some elements provided by NASA's Goddard Flight Center. But a wide field, 3.4 minutes by 3.6, multi-objects near infrared spectrometer covering wavelengths of 0.6 micrometers to 5 at spectral resolutions of R100, R1000, and R2700. So NIRSpec will enable large spectroscopic surveys of astronomical objects like stars or distant galaxies, and made possible by the powerful multi-object spectroscopy mode, and it's capable of obtaining spectra of nearly 200 objects simultaneously. So it will support Webb's 4 main science themes by providing low, medium, and high resolution spectroscopic observations. So this is quite large. It measures 1.9 meters by 1.3 by 0.7 and weighs approximately 200 kilos. It's an all reflective system with a total of 14 mirrors, 7 interchangeable dispersive elements, and 8 interchangeable filters. And this one was built by, developed by ESA with Airbus Defence and Space, GmbH as the prime contractor. This is a picture from September 2013. So again, this is Europe reached another milestone in its contribution to Hubble's successor, the James Webb Space Telescope. So they completed the build in 2013. And its job will be to determine the age, composition, movement, and distance of objects in its field of view. And the expectation is some of these targets will include the very first stars to shine in the universe. And that would mean picking up light signals that have traveled across space for perhaps 13.6 billion light years, something which Hubble cannot do. And NIRSpec is critical for this new capability and represents 10 years of design and manufacturing endeavor. So that completed Europe's major industrial commitments to Webb when this was delivered. And the other instrument from Europe was MIRI, which was delivered a year earlier. So that was Jonathan Amos from the BBC reporting in September of 2013. And here we can see it without its cover. And so an interesting aspect of NIRSpec's design is that nearly half by weight of the instrument is made from ultra-stiff silicon carbide. And the unique feature of silicon carbide is it allows them to make structures and mirrors out of the same material. So that helps with survive the transition from going to warm to cold, as there's no deformation, and it gives a very good stable alignment on the optics. So NIRSpec uses a system of tiny gates to select objects to study. So it's difficult to do all this stuff without having any problems. And unfortunately, I think this was an area, a mix of funding, technical and management shortcomings resulted in years of delay, ballooning costs. And I think this was one of the aspects that had to be redesigned, because NIRSpec left Germany with 2 US provided components that did not meet the required spec, and which were going to have to be changed before launch. And these were the instruments, infrared detectors, and the system of microshutters. But again, partly due to the delays, I think the performance of the detectors degraded over time. So they'll be replaced with modified designs. And at the time of this report, which was again 2013, that was still in development. And the microshutter array uses 250,000 tiny gates to select the object of the sky for study, and up to 100 at a time. And some of those gates were getting stuck in the open position after testing. So again, the Goddard's experts had to come up with a solution, which again in 2013 was well advanced. So it wasn't all plain sailing. And then we've also got this fine guidance sensor and the near infrared imager and slitless spectrograph. So used to stabilize the line of sight of the observatory during science observations. And it's looking at wavelengths between 0.9 and 5 microns. And this has got a field of view of 2.2 by 2.2 arc minutes. And again, another view of the fine guidance sensor. I think the final instruments in the package was the MIRI, the mid-infrared instruments. And this is a mid to long range, long infrared wavelength range. So from 5 to 27 microns with a field of view of 1.3 to 1.7 arc minutes. And this was all put together and tested by Webb Space in Oxfordshire. As I said, this was arguably the most versatile of the 4 instruments, much wider range of detectable wavelengths than its peers. And it went through rigorous mechanical and thermal testing at Rutherford Appleton Laboratory in Oxfordshire. So this has also got the combined infrared camera and spectrograph, so resolutions of 100 or 3000, covering wavelengths of 5 to 28 microns, and it also includes a coronagraph. Just realized to skip some of these. Now, we're all going to have a bit of filter envy here. This is a filter wheel mechanism inside MIRI, and we obviously need to work for perhaps 20 years. So I'm sure that cost a few pennies. Now, this is another interesting device. It's part of MIRI, and again, UK technology here. So Gillian Wright was director of the UK Astronomy Technology Centre, has got the flight spare, Basically, this mirror will slice up the incoming light. It's about the size of a 50p coin, and basically, what's it say? So it acquires the image of the sky, but it chops up the light from the stars and then sends the light to the spectrograph. The device can reveal the chemistry, temperature, density, and velocity of the targets under study. But it's not just one point in the image, but every point across the image, all at the same time. So it's like 2D to 3D in what they call a data cube. But yeah, just an amazing bit of technology. So we must be getting close to launch because we get a new launch logo. But one last view of Webb on Earth as it disappears behind the nose cone of the rockets. And then its stowed configuration to fit into the nose cone of the Ariane 5. So we could see how big Webb was. So yeah, quite a large structure there we have. And then finally, lift off at 2020 UTC on Christmas Day 2021. No, I'm not sure. Did the audio come through properly on the last clip? So
It was very quiet.
Yeah. Let me just stop sharing my screen quickly, and I'm going to reshare once I double check I've got the right audio settings selected.
Yeah, I think, Dave, it is very quiet. You just need to just turn your laptop up as loud as it'll go.
Okay, top.
Yeah, I did have the right setting checked, but on the other hand, that video, it was very, very quiet anyway. So hopefully this will be a bit better. I know we're running a little bit late here, but I think it's worth watching this. So this is about 5 minutes. So if anyone wants to grab a quick drink, now's the time.
Thumbs up from Jean-Luc Voyer. All systems are go. We're inside a minute now. T-minus 30 seconds and count. Standing by for terminal count.
À tous de DDO, attention pour les décomptes finales. 10, 9, 8, 7, 6, 5, 4, 3, 2, unité, top.
And we have engine start. And liftoff.
Décollage.
Decollage, liftoff from a tropical rainforest to the edge of time itself. James Webb begins a voyage back to the birth of the universe. Punching a hole through the clouds, 20 seconds into the flight. Good pitch program reported. And let's go down to the floor in the Jupiter Control Center to Raphael Chevrier of Arianespace. Raphael, so far so good.
Hi, Rob. So far so good. Everything is nominal, as we say, when attitude and trajectory of the Ariane 5 is going perfectly well, as you can see also on the.
About 11 minutes from now, telescope controllers at the Space Telescope Science Institute will be sending commands to prepare James Webb for the initial series of commissioning activities that will lead to the deployment of its solar array and the initiation of generation of electrical power for the telescope. James Webb, of course, will be traveling well beyond the moon to a distance of about 1 million miles away from Earth, settling into a highly elliptical halo-like orbit to begin its astronomical observations. And again, as we mentioned earlier, at the time of observatory separation, Webb will be at an altitude of approximately 864 miles, statute miles, traveling some 21,000 miles an hour. James Webb is about 4 minutes away from separating from the upper stage. And at that point, it will be on its own. And again, those milestones that we discussed a bit earlier in the broadcast will begin to be followed carefully by the telescope controllers at the Mission Operations Center, the MOC as it's called, at the Space Telescope Science Institute in Baltimore.
Séparation Webb Space Telescope. Go Webb!
We do have confirmation of observatory separation. The James Webb Space Telescope, amidst applause here in the Mission Control Center, now taking its first steps in pursuit of cosmological discovery. And there is the view from the upper stage camera on the Ariane 5, looking at the James Webb Space Telescope as it moves gently away from its launch vehicle.
Fantastic pictures of this telescope.
Go Webb, go Webb.
Yes, go Webb.
Ironically enough, as we marvel on this view from the upper stage camera, this will be humanity's last view of the James Webb Space Telescope as it moves to its workplace about 1 million miles away from Earth.
Yes, you're right.
And there we saw the solar panels deploy.
Fantastic pictures. Yeah.
There is the solar array having been deployed. James Webb now has its array out as we stand by for confirmation that it is power positive.
Hey, Rob.
And there it is. There's your critical call. James Webb not only has legs, but it has power as it begins its journey and the commissioning activities to follow.
So I thought that was pretty impressive. Unfortunately, at the time, if you were watching this live, that downlink was pretty glitchy. But ESA did clean up the sequence, and it also got set to music by Charlotte Hatherley. Never heard of her, but they put it together with a piece of music they call Lonely Waltz. Would recommend going and watching it. It is quite moving. So now it's launched. We've got deployment of various aspects. So we could see at sort of launch plus 3.2 minutes, we have the fairing separation. And at plus 33 minutes, that solar panel deployment. Or obviously at 30 minutes, we separated from the launch vehicle. And then a number of these, the next key one, of course, was the gimbaled array for maintaining communications back to Earth. And then we'll have the sequence of the Sun Shield deploying over a number of days, then the secondary mirror deployments, the primary mirror, and the wing deployments until finally it's fully deployed. And then finally sort of insertion into the L2 orbit. So as we saw on day one, the solar array got deployed. And day three, start of the Sun Shield pallets, and the fairly slow process of unfurling the Sun Shield, and eventually separating the 5 layers. And then on the 5th of January, which by my reckoning would have been day 12. So some of those graphics, the days were a little bit out. But again, BBC reporting that the Sun Shield was fully deployed. And now they can start concentrating on packing the mirrors and proceeding with the rest of the deployment. So yeah, secondary mirror held out by some 3 8-meter booms rather. And I think that was reported on the 22nd of January. They were fully deployed and locked in position. Yeah. And then the wings for the primary mirror deploy. So it's folded up a bit like a trestle table before, but pull it back out. And the 8th of January, which again would have been day 15, we've got the deployments of the of everything there complete. So it's now ready for focusing. So I mentioned before that NIRCam is going to be part of the system that will do the alignments. So the first thing they would do is point at a star field with lots of stars and check that NIRCam is working fine. And then the adjustments can bring. So if you recall, back at one of the very first slides, we were talking about obviously the 18 mirrors. They're expecting to see 18 different stars, which is of course what we can see in this graphic. But the next process is trying to identify each of these. So at the time they were pointing Webb, it's the star HD 84406, and we'll see where that is in the sky a bit later on. But this was their first star they looked at for an engineering purpose to start the alignment. We have a little short animation here of this first step of the. No, back one. Let's try that again. And if you counted them, you would have noticed there were 18 stars in that field. So the next step is further segment identification. So one by one, the 18 mirrors are moved to determine which segments creates which segment image. Then after matching the mirror segments to the respective image, the mirrors can be tilted to bring all the images into a common point for further analysis. And this arrangement they call an image array. So hopefully this graphic will show this a bit clearer. So you can see as they move the mirrors, various objects are moving. I'm getting a bit of an echo. Are you all on mute? So we can see here that as they identify each one, they're going to tilt it so that the image they see, the stars line up with the 18 segments of the primary mirror. So we now next go to the segments alignment, having identified them. And this is going to correct the large positioning errors of the mirror segments. So they begin by defocusing the segment images and moving the secondary mirror slightly. Then there's a mathematical analysis called phase retrieval that's applied to the defocused images to determine the precise positioning errors of the segments. And adjustments of the segments will then result in 18 well-corrected telescopes. However, the segments still don't work together as a single mirror. So next animation hopefully will show that. And then we come on to what they refer to as image stacking. So to put all the light on in a single place, each segment image must be stacked on top of one another. In the image stacking step, the individual segment images are moved so that they fall precisely in the center of the field to produce one unified image. And this process prepares the telescope for the next step of coarse phasing. So the stacking is performed sequentially in 3 groups. So they'll do the A segments first, then the B segments, and the C segments. And we'll see that in this animation now. So it's the A segments being merged into a single image in a couple of steps. And then they'll bring the B segments in. And finally, the C segments. Well, it doesn't look like that played fully to the end, but never mind. It was close enough. I think you get the drift. There was one final graphic on there that was a bit brief, but so this coarse phasing, although the image stacking has put all the light in one place on the detector, the segments are still acting as 18 small telescopes rather than one big one. And the segments need to be lined up with each other with an accuracy smaller than the wavelength of the light. So conducted 3 times during the commissioning process, coarse phasing measures and corrects the vertical displacement, so that's the piston difference, or the Z actuation of the mirror segments, and using a technology known as dispersed fringe sensing, NIRCam is used to capture light spectra from 20 separate pairings of mirror segments, and the spectrum will resemble a barber pole pattern with a slope or angle determined by the piston difference of the 2 segments of the pairing. And in this simulation, the barber pole patterns are created by the dispersed fringe sensor, indicating a large piston error or a small piston error. So let's have a look at this animation. Just begin to see that barber pole effect. So that was the course phasing step. So we'll now move on to the fine. Using if I can get the right button. And this is also conducted 3 times, and directly after each round of course phasing, and then routinely throughout Webb's lifespan. And these operations measure and correct the remaining alignment errors using the same defocusing method applied during the segment alignment. However, instead of using the secondary mirror, special optical elements inside the science instruments are used, which introduce varying amounts of defocus for each image. So ranging from -8, -4, +4, and +8 waves of defocus. And again, a short animation. I'm sure we'd all wish our telescopes was well aligned as this. And then finally, in this part of the alignments, and this one we might have to play it a couple of times. It took me several views to really see what was going on. But basically, what we've got, oops, get this laser pointer to work. Come on. There we go. So if we look at the stars in the field of view for the NIRSpec, we can see they're a bit blurred, a bit fuzzy, and maybe not particularly central. So we've got the FGS here. This is MIRI over on this side. This is NIRCam. And this is the NIRSS, the slitless spectrograph. So in the animation, sort of watch for what's happening in these boxes, but also watch to see what's happening with the secondary mirror. As I say, we may have to run it a couple of times if it doesn't become that apparent. So we can see the secondary mirror moving a bit there and the images on the different instruments, but they do finally go from the fairly blurred points to nice points of light at the end of the process. Shall I run that again, or people happy? Okay, one more time. It's only short. As I say, it took me a few watches to actually see what was going on with that particular one. And then finally, or not finally, we've still got a few to go, but we get to doing a mid-course correction burn. So from launch, which was on the 25th, of course I got one time in UTC and another time in Eastern Standard. So the first correction burn was actually on the day of launch. And it lasted 65 minutes. So the actual burn was about 20 minutes shorter than the planned burn, which was of 82 minutes. And it added about 45 mph or 20 meters per second to Webb speed. And this burn was one of 2 milestones, as I mentioned before, that was time critical. The first being that solar array deployment, which happened shortly after all we saw during that launch video. So this burn adjusts Webb's trajectory towards the second Lagrange point. And after launch, Webb needs to make its own mid-course thrust correction maneuvers to get to that orbit. And this is by design. And Webb received an intentional slight underburn from the Ariane 5 that launched it into space. And that's because it's not possible to correct for an overburn. And as I said before, the last thing they want to do is actually push Webb beyond L2, because then it would be lost, it would be irretrievable. And of course, you know, even if they could turn it around, turning around would destroy the optics. Then there was a couple of days later, there was mid-course correction burn number 2. So 60 hours after liftoff. This one only lasted 9 minutes and 27 seconds and added just 6.3 mph or 2.8 meters per second to Webb speed. And then finally, we have launch day plus 30. So January the 24th, they did a 5-minute burn of the thrusters, which actually inserted it into the halo orbit. So I think I mentioned that the L2s are one of the 5 gravitational sweet spots. And the advantage, of course, being that out there, it's not really subject to big swings of temperature and light. So vital for this mission as it's designed to look at the cosmos in the infrared. So actually the flawless precision of the Christmas Day launch by Ariane enabled the 3 burns of the onboard thrusters to put Webb into the L2 using far less of its propellant than planned. So much so that they think it may have extended the capable life from the 5 to 10 years to possibly 20 years, just by that fuel saving alone. But more robust numbers will come out once the flight dynamics team have had more time to do more analysis. But yeah, the right way to get there. And as reported by Jonathan Amos on the 11th of February, Webb begins to focus his big eye. So if we count the dots, we should see we got 19. Sorry, not 19, 18. Where did that 19 come from? And then one of the, I think NIRCam took this selfie. This is before they'd actually done the focusing, I think. It was actually created using a specialized pupil imaging lens inside NIRCam. In the image, one of the mirror segments glows more brightly than the rest because it was pointed at a bright star, while the 17 others weren't at the same alignment. I mentioned it was HD 84406 in Ursa Major. So courtesy of Sky Safari, we can see where HD 84406 is in the sky. And as NASA tweeted, Starlight, Star Bright, the first star Webb will see is HD 84406. And then quite recently, we had the news that Webb's fully focused, and comments being that it's beating all the expectations that they had. So very pleased. Now, recently I posted a picture I'd taken with my Muon, and somebody made a comment about, oh, the diffraction spikes were like James Webb. So some of you may have been in on the conversation, but does anybody know why we have this diffraction pattern from Webb? And why I have the same diffraction pattern on a Takahashi Muon? Well, the answer is the number of veins holding the spider. In the case of my Muon, and there are 3 veins. Whereas if we recall how many booms are there holding the secondary mirror on James Webb? We've got 3. So that accounts for this particular diffraction spike pattern. And as Dave and I were discussing last night, how I didn't appreciate that, yes, the sharper the diffraction spikes, that's also a good indication of how well how good the focus is. And again, if we look at this image, and oh, come on, where's it? If we look down here, one of the background stars there is displaying a nice diffraction spikes as well. And then again, it's a little graphic. I'll keep that going. So 13th of April, latest report was that the MIRI instrument has got super cold. And this is the one that is, it's not just actively cooled, passively cooled rather, but it does have a bit of active cooling. So that's a chilly minus 267 Celsius, or just 6 degrees above absolute zero. And now we're in the final stretch. So 29th of April, these images of the different instruments and their fields of view was published, showing nice star detail in each of the instruments. Didn't actually find a date on this, but again, MIRI spying the Large Magellanic Cloud. And just before we kicked off this evening's meeting, I logged on and had a quick look, and the latest news as of 2 days ago was that James Webb has done its first practice tracking of asteroid. So no image or anything, but just the text to say that they've successfully managed to track a moving object. So it's not just that they can position and find guide on a distant star and take lots of deep images, but they can also track moving objects.
I was going to ask that question there, Bob, because that asteroid is 4.3 million miles away from the Earth. I was going to say, did anybody track it the other week? But if they've got this and they've got it, do they track it? I
don't know. That would be the one they were tracking, but potentially for those, anything that's sort of near Earth crossing, I'm sure they will. If it's, but you have to remember, of course, is it in the portion of the sky that Webb can see at that time of the year?
True.
So near the end now, so we're now looking at some of the spin-offs. And if you recall, I asked you when we looked at the fine guiding sensor, and I said, oh, pay attention here, because this thing called a sidecar, and it gets the acronym from a system image digitizing, enhancing, controlling and retrieving ASIC. And it performs high fidelity analog to digital signal conversion at cryogenic temperatures. And this was one of the things that this technology actually came up in time. So it was actually used on the advanced camera for surveys that was repaired during the Hubble SM4 servicing mission. But each of these chips amplifies the voltage from the faint detector analog signal, converts it to a 16-bit digital signal, and organizes it into packet before sending other processing storage electronics on Webb, so that it can then be transmitted to Earth and be reconstructed into images and spectral information. And these ASICs are programmable, so their functions can be tailored to meet needs of particular science instruments and observations, and more likely not just restricted to astronomy. So the company, another company that was some of the spin-off technology was an outfit called 3D Technology, and Webb provided them their first commercial contract to develop a phase cam interferometer, which was used in testing and setting up the primary mirror. So they also developed several new types of high-speed test devices utilizing pulse lasers that essentially freeze out missions at the effects of vibration, which they sometimes suffer from. So they've gone on to generate quite a wide revenue from not just astronomy, but from aerospace, semiconductor and medical industries based on technologies developed for Webb, including new optical measurement devices that will allow ophthalmists to get a much more detailed information on the shape of your eye in seconds rather than hours. So as usual, sort of spin-offs coming from the all the research and development that goes into something like James Webb. And then finally, just to reiterate, that Webb was an international collaboration just from the beginning. So in addition to the States, there were 14 countries involved in building Webb, including Austria, Belgium, Canada, Denmark, France, Germany, Ireland, Italy, the Netherlands, Spain, Sweden, Switzerland, and the United Kingdom. And additional member states of Europe also contributed via the ESA. NASA is the lead party or partner on the project, working in collaboration with ESA and the Canadian Space Agency. And the Space Telescope Science Institute conducts the science and mission operations from its Baltimore, Maryland headquarters. And it's obviously the lead agency is NASA with overall responsibility for Webb. And what we have here in the image is basically a Hubble-style visible light image of the pillars of creation, and then the kind of view that you would see in the infrared. And again, just a map showing where all this international collaboration is across the globe. And more than 120 American, European, and Canadian universities, organizations, and companies in 14 countries and over 29 US states contribute to Webb. So what's next? I guess it's watch this space. And as I mentioned, there's some URLs of various sites that I acquired, material for this presentation from. And as I mentioned, in particular, I really like this, the Breaking Taps YouTuber. He's got some really interesting stuff on not just Webb, but and the elements of Webb are another great source of short video clips, of various aspects. If anybody wants to do any more detailed digging into this, the links will be here in the presentation if you can't find them yourself, Google. And that about wraps it up, I think. So just a few acknowledgements that I've got various sources, including all these websites, and on the images I've tried to credit where they've all come from. And I think finally you can breathe a sigh of relief, and a little bit longer than usual, but that's it. So thank you for your attention.
Yeah. Yeah, well done, Bob. That's very good. Thank you very much. Very good.
Thank you. Thank you.
Fascinating. Thank you.
Great stuff. Great stuff.
Oh, that's brilliant.
So I will be able to answer any questions, but are there any? And we can maybe do a joint.
There was one I was going to ask you what beryllium was, but I've actually looked it up on my phone, and I looked up what beryllium was. And I thought, oh, brilliant. So
Yeah.
I didn't know what beryllium was. Now I see.
I should have mentioned that, because
So what you got?
I presume you all have your periodic elements chart right by the side, don't you?
No, but I looked it up and I thought, oh, I wonder what beryllium was, but it's lightweight material. And
No,
I thought it was man-made, but it's actually.
No. It is extremely, the conditions to produce it are extremely rare.
Yeah.
Because if you go through the normal fusion cycle, you go from hydrogen down to iron. But the fusion stops when you get down to iron. All the other elements are created during supernova explosions. But beryllium isn't. Beryllium I can't remember the exact detail, but it requires a cosmic ray strike during a supernova with some of these elements to actually form beryllium, which accounts for it being extremely rare. But again, if you go and look at some of the elements of Webb, they do a really good series of short videos on where beryllium is found, how it's mined, how it's processed, and the whole process that it went through in the manufacture of those the segments for the primary mirror. Because of course one of the problems with polishing something like beryllium is it's extremely toxic. So, but the lightest metal there is.
Strong as well.
Yes, and again, very stable across the whole temperature range. So,
Oh,
so yes, Keith.
Couple of questions. One, how do they focus it? I know we talked about aligning the mirrors. How do they focus it? And two, there was a steering vane on it. Do you know how that works?
I think that was the stabilization vane.
Was it a stabilization?
Yeah, if I go back to the original.
It offsets the
Reaction.
photons pushing against the solar panel. So it counteracts that.
So
that's what that particular panel does. If that's the one you meant.
Yeah, I thought it was a steering, but if it's stabilization. So does it?
This one.
Yes, this at the back there.
Yeah.
So if light is striking this near side, how does that work then?
Well, you got the light is striking the solar panel.
Yeah.
And it's also, so it's trying to push that way. And so it's also going to be striking that steering panel or stabilizing panel. And so the net effect is they cancel each other out, I suppose.
But as I said, they do have to do orbit maintenance, so that they track how it's behaving over a period of 19 days, and then they do the correction burn. So I'm sure it plays a big part in that whole process of maintaining, so the attitude control of Webb.
I know that when you were saying earlier that it's solar powered, and that's what made me think about it. And then they were saying about thrusters to do things. And I thought the thrusters aren't going to last that long. But the way you're explaining that there gives me an idea of how they're doing it.
And well, they do have fuel for the thrusters, so but the thrusters aren't electrically powered. It's all a chemical reaction. So, but again, that is the limiting factor for the life of most spacecraft. And for those that were involved with the not Argus, was it Argus project? I can't remember now. Brain's gone dead. But no, the MEV, where they sent the refueling vehicle out to the geostationary satellites to refuel one of the comm satellites, because that was extending, because again it was running out of fuel. So stuff that's in geostationary orbits, we now have the technology to go and refuel them to extend their life. Whether in the next 10, 15 years, similar technology will be available to go out and service something like Webb, who knows? Whether it's even been designed to have the ability to be refueled might be the other issue. But,
and how do they focus it, Bob?
I thought the focusing was all part of each instrument, I think, probably has its own focusing mechanism. So if I can go back, I'm just trying to picture which one it was. Give me a second, let's see if I can find. So I think on this, the fine guidance sensor, on this one, we can see we've got the fine focusing mechanism with the fold mirror. So I presume the other instruments have something similar, but they have a focusing mechanism.
So the instrument effectively moves to provide focus. Is that what you're saying?
Or some optics within the instrument. Don't know, is the honest answer.
Okay, so there might be more optics in the optic train.
Well, certainly on the which was at the go back to which slide was it? This one wasn't. MIRI. I think on this one they talk about it having. I'm just looking at my notes on to see if it gives any clues. No, I don't see any mention of focus in my notes. I'm sorry.
So I think it's part, Bob. I think it's part of that initial setup routine where they're using the actuators to align the mirrors,
yeah.
And then because there was an announcement saying it was now focused, right?
Yes.
And then I think you'll find the fine focus mechanism on each of the chips, the set or each of the different instruments they've got allows for a slight adjustment if they need to. But really, the main course focusing is now done.
Because we saw that in the after the course phasing, we went to the get back to it. Went to the fine phasing, and when I think with this one, is this the right one? Next slide. Because if you look at what effectively would be the full height half width,
yeah.
So you think there's enough movement in the primary mirror,
yeah.
to account for focus.
So why is that not playing? Is the one that showed it? But yeah, if you were to see that kind of plots on your system and a nice big spike like that, you're only going to get that when you're in good focus. And as Dave said, that was all basically achieved via the manipulation of the primary and the secondary mirrors. But I'm sure each instrument must have its own fine focus mechanism as well.
It will, partly because they all operate at different wavelengths.
Yeah.
So their focal plane will be in a subtly different place.
Thanks, Trevor.
So Bob, do you know how big those filters were?
No, I didn't spot that. But probably, well, given, hang on, let's go back to the.
I guess, do we know how big one of the
was
imaging cameras is? It's going to have to cover that, isn't it?
Yeah. Yeah, unfortunately, there's nothing on there to give you any kind of scale.
Those screws look M4 or M6, Bob.
Yeah, so they're probably only 50 mil, 2 inch. What do you reckon, Mike?
Yep.
Do you like the detail mechanism?
Yeah, I would have said 50 mil.
Yeah.
It's quite small, isn't it?
Well, this is for the mid-infrared thing, isn't it?
Yeah.
So you've got you're talking about an array of microbolometers in a chip.
I guess I'm used to seeing the filters on the Isaac Newton, and they were huge.
Yes.
Dinner plates.
Yes, they were.
Yeah.
When John pulled them out the cupboard, was banding them around. They go, oh, they're only 30 grand a piece.
See, what I found really interesting was the shaped ones, which I think are the coronagraphs.
Coronagraphs, yeah.
Mm-hmm.
That's exactly what I was thinking, because you can see the diffraction pattern that you'd expect as well on aspects of them.
I think the middle one there at the front is a reindeer.
Yes, you're probably right.
All Astrodon, are they?
Wouldn't surprise me.
Bob, do you know, towards the beginning, you showed the slide of the 5 layers of the heat shield.
Yeah.
And a graphic that went with it. And you said that the first 2 layers have an extra coating on it.
Yeah.
Do you know what the sort of percentage difference between each layer is of the heat it needs to remove?
No, I was trying to find a graphic that's, oh, actually, where was the other one?
Because the graphics kind of implied that
there was another
they
one.
weren't all equal. The first couple of layers took most of the heat out.
Yes.
And then the extra layers just took a bit more out each time.
Yeah. I think I've got 2 points of reference there. I think there was that one. I know where it was. Excuse me. So that was one.
Yeah.
And again, that's sort of implying that the bulk of the heat is dumped from this between the first and the second layer.
Yeah.
And then it sort of gradually reduces down. But I don't have any values for what the range is, although there was one which I think it did show, which was that graphic, which was that slide. Sun Shield.
But it looks like it's going to be exponential, isn't it? It's not going in a simple ratio.
No. Yeah, but as I said, if you had 200 kilowatts coming in, you're only getting 1 watt coming out.
Yeah,
that effective. I shall have to update the slide when I find the answer. But thanks for the question, John. Anybody else got any thoughts? Or shall I? I'll stop the recording and promptly delete it. No,